So this video will be for Chapter 11, Part B, and we're going to begin at 11.4 with membrane potentials. When we're focusing on the membrane potential, we're going to be talking about the resting membrane potential specifically, just like we talked about in Chapter 3 with general cells. What's interesting about the resting membrane potential for a neuron is it has the ability to rapidly change. And this rapid change is going to be called excitable, which gives it a charge. So we're going to be focusing specifically on this charge throughout this entire section and essentially the rest of the chapter. So this charge is going to be based on the concentration of ions that are moving inside the cell into the ICF and the concentration of ions that are moving outside of the cell into the ECF, or the extracellular fluid. So just remember that whole movement of those ions we're going to talk about again. So this works because of basic principles of electricity. So positive charges are attracted to each other. We have negative and we have positive, and they like to move towards the other. Energy is going to be required to make these charges separate. And the way this is going to work as separate is it's going to be across a membrane. So when we have that cell, and we've got this membrane that right here that ion has to move across and be able to transfer from point A and or point B, you're going to require energy. And that energy is going to help move these functional processes along. And when we do that energy, we're going to release some energy. And because of that, it's called potential energy. And so we talked about that in Chapter 2, but we're going to be working with those potential energies for the next little bit. So some general definitions of electricity. So one of the terms is going to be voltage. And voltage is going to be the separation of charge. And that separation of charge is giving us that potential energy. So just like I drew earlier, here's your plasma membrane, and we're separating a positive charge and a negative charge. And if we have that plasma membrane and we're separating a charge, we are creating a difference on one side versus the other. This is called the potential difference, or potential. So that's where the resting membrane potential comes into play. And when this is occurring, you're going to have movement of ions because that potential is great, and then it's going to give us a direction or a flow, which we're going to talk about next. So the bigger difference you have, the higher voltage. So when you get batteries that are going to be like millivolts, it's not a lot of voltage. It's a little bit of voltage, but then you get those big Mac Daddy batteries, and it could be a 5-volt battery. That means that there is a larger separation of charge. There's more potential. You get more work out of it, so it'll last longer. Another definition is going to be current. Current is the flow of ions from one place to another. So it's going to be the movement of these ions that is giving us this charge. And this is what gives us work, or the ability to do items and work. And flow, or the current, or the movement, is going to be due to both voltage, the separation, and the resistance. And resistance is going to be what is in the way to the movement. Resistance is the hindrance to the charge, what is blocking the movement of the ion. In our particular case, when we're talking about a cell, in particular now we're talking about a neuron, we are talking about this resistance is going to be the plasma membrane. So it's the plasma membrane that is separating the two charges, extracellular fluid and intracellular fluid. And if this plasma membrane right here is blocking this charge, we're hindering it. It's our resistance. Therefore, we have a potential across that plasma membrane because our current can't flow. So it's all working nicely together. Okay, if you are a physics person, you may have heard of Ohm's law before. Ohm's law essentially connects the relationship between voltage, current, and resistance. And Ohm's law is going to be current is equal to voltage over resistance. So essentially, the amount that the ions can move, the current, is going to be equal to how much potential energy is stored up divided by whatever is in the way and how big that thing is. So the movement of ions can only move if the voltage, the potential energy that's stored, and the thing that is blocking the path are at the right level of proportion. So I equals VR is going to be the term you're going to see. We're not going to be doing math for Ohm's law, so you don't necessarily need to memorize this verbatim, but you need to know what's going on. So what is going on is this basic idea of membrane channels. When we have this ability for our membrane ion channels, which we've talked about, we've got voltage gated, we've got leak channels, chemically gated. When all of these membrane ion channels, specifically at this point, we're going to be talking about the voltage gated ion channels, they're going to serve as selective membrane channels. They will only let certain things through. So a potassium ion will only go through a potassium one. So we've got the leak ones, which we've talked about, which are going to be always open, and those gated ones, which are going to be chemically or voltage or mechanically gated. We're going to be spending most of our time in this chapter on voltage. But what that means is that this now has a bridge in order to go across our plasma membrane. So before we move on, I do want to hit up this equation right here. So with Ohm's law, when you've got current equals voltage over resistance, this is basically what it means. If your current is increasing, so the ions are moving, your potential energy is going to increase because current and voltage are both on the top of the equation. Think about it like that. When you increase the resistance, when you increase this guy right here, you're going to decrease the current. It is a opposite effect. So if I increase the block, if you go from a teeny tiny little fence that you can step over to a concrete 10-foot wall, you're not going to be able to step over. The likelihood of you moving across into the yard of your neighbor is less likely going to happen. So that resistance, the block that is in the way, if that increases, then your current will actually decrease. So that's what's going on in that world. And our membrane is going to be that resistance. Okay, our voltage is going to be whatever different concentration of ions we're going to have. So you're going to have a voltage based on your calcium, a voltage based on your sodium, a voltage based on your chloride, a voltage based on your calcium. Potassium, sodium, chloride, and calcium are going to be the main drivers for this plasma membrane. That's voltage. Wherever these concentrations are, high or low, that's giving you that voltage. And when they start moving, you're going to have that current. So this is where you can kind of see what is going on. The current is the movement across. The voltage is the fact that there's 5 versus 2, and the resistance is the plasma membrane. So that's what's going on with this world. Okay, so looking at these gated channels, the gated channels are opening because something is telling it to open. There's a key that opens it. When you have a chemically gated channel, a chemical is going to be opening it somehow. That could be sodium, that could be potassium, because those do fall into the chemical category of the ion. When you have a voltage gated channel, these are opening specifically in relation to the charge. So if it goes from negative 50 millivolts and then it changes to negative 55 millivolts, that is a change of 5 millivolts. That may be enough to open the gate. It could not be, but a voltage gated is opening up based on the potential that is going on with the plasma membrane. Okay, another basic premise of electricity is that when you open these channels and the gate is wide open, ions move rapidly. They move very, very, very quick. And we've talked a lot about this, but chemical concentration will go from high to low always. Electrical concentration will go from high to low, but it will also go towards its opposite electrical charge. So that means if I have a high concentration of calcium, it will move in the direction from high to low. But if I have a lot of positives, a high concentration of positives, it will also go towards negatives. So we will have both things occurring. This is a bit of a review because we've also talked about this in chapter 3. This is just a little bit more of the physics behind the electricity. So because we have the options and we have both the chemical concentration here and the electrical concentration here, we get the term electrochemical gradient. So an electrical chemical gradient is the electrical change and the chemical change and what things are happening when all put together into one big soup. Chemical gradient is going to be the movement of the ions, so we are moving from high to low ion concentration, whereas an electrical gradient, we are moving from high voltage to low voltage, or this low voltage could be negative. So think about high versus low as this could be -50 and this could be -40. That is still closer to 0, so that is still low. So think about it that way. It doesn't have to be necessarily to a lower number. It's in relation to 0 on the number line. Okay, when we're generating and looking at the resting membrane potential, again, RMP is a number that is telling us what the voltage across that plasma membrane is. It's going to always be a number, and in a neuron and in a cell, it's always going to be millivolts. So when we generate it, we can measure it. And in a neuron, the resting membrane potential is approximately -70 millivolts. This is slightly different than what we talked about when we talked about a general cell in chapter 3. So that was kind of a general overall. This is specific to neurons. In this -70 millivolts, basically the ions outside of the cell in the extracellular fluid, there are going to be more negative. So in that sense, it is, more positive. Inside the cell, it will be more negative relative to the outside. So we have outside, it's going to be slightly more positive. Inside is going to be slightly more negative. And there's a little note that it could vary from 140 to 190, but -70 is the number we land on for a neuron. Because there is this potential, these neurons are considered polarized. And this polarization is going to be generated by two things: the ion concentration of intracellular and extracellular fluid, and how permeable the plasma membrane is, what the resistance looks like. So when we look at that, here is something called a voltmeter. If you were in lab, and it may be in the Mastering A&P, you actually stick a little electrode into a neuron and you can register what the membrane potential is. It's very, very cool. But when we're looking at that, the differences in ion concentration are the first thing that is controlling the resting membrane potential. Again, this is an overview because we've already talked about this in chapter 2, so much so that that's what homework 1 was focusing on. So go back and review homework 1 because that is exactly what this is. So the extracellular fluid outside has a higher concentration of sodium. The intracellular fluid has a higher concentration of potassium. And then they both are kind of balanced by an ion. Sodium is balanced by chloride, and potassium is going to be balanced by a protein that's kind of negatively charged. So this is our general. This is going to be after our fancy dandy sodium potassium pump. This is our situation after we have our sodium potassium pump. This is where we land. And when we land here, potassium is the most important role in establishing our membrane potential. Look at focus figure 11.1 in your book or go back and review homework 1. So when we're doing this and we are looking at calcium and sodium concentrations inside and outside of the cell, and then how often things and if they are able to move across. So we said it was based on the concentration of ions, but then we said the second thing was whether or not the plasma membrane was able to have things pass through it, how permeable it was. So it's generated by that differences in the ion concentration and this permeability, basically saying that it kind of likes sodium to come through, but it really likes potassium, so much so that potassium is 25 times more permeable to sodium. So our resting membrane potential has sodium and potassium on either side of the cell in very high concentrations. But your potassium likes to move across and can do it way quicker and way easier. So that's going to be driving the differences in our plasma membrane permeability. So potassium is our chief ion that is causing our resting membrane potential to occur. So what is happening with this is when we are after our sodium potassium pump, This whole process is stabilizing that resting membrane potential to be -70. It is setting the stage. So it is pumping your ions, your sodium and your potassium, 3 and 2, across the plasma membrane. If that doesn't strike a bell, go back and look at that. That's also in chapter 3, I apologize. That sodium potassium pump is stabilizing, creating this concentration gradient, walking away, and now we have a difference in our ions on either side of the cell and a difference in plasma membrane. So your resting membrane potential is essentially stabilized by the sodium potassium pump. And if nothing is happening and it just stays like that, then your ions are going to just naturally flow. Some sodium will flow across, some potassium will flow across, but for every 1 sodium, you get 25 potassium. And that's at rest. That's if nothing is happening. But once we open up a gate or open up a door, things move quicker. And that's what we're going to talk about with the neuron. So once we are looking at a membrane potential, anytime we're going to have a change, your potassium will flow more easily down that concentration gradient. So as we're going down this membrane potential and we have a change, it will occur and create 2 different types of communication. So basically, this should be, when we are looking at what our membrane potential does, it is essentially a communication. When the ion moves across the cell, it is telling or it's causing something to occur. So when that is changing, it's essentially producing 2 types of signals. The first signal is a graded potential. Note potential because there's still a separation of charge. A graded potential is something that is going to be only incoming. It's only taking in news. It is not giving out news. You're only taking in information. And it's going to be over pretty short distances. It's not for a sustained length or distance of time. And then you have something called an action potential. An action potential is going to be the outgoing signal. It is you now telling something to someone. And it's usually over a pretty long distance. So we've got a graded, which is short and only incoming, and an action potential, which is long distance and outgoing. So it's kind of what is happening with this resting membrane potential and the communication that occurs from it. So when we're talking about our membrane potential changes, we are talking about them relative to a resting membrane potential. So we've talked about these terms before. So the terms are depolarization and hyperpolarization. So when we have these changes in our membrane potential, it is telling us what direction the graph is going. Depolarization is a decrease. But if we look at a number line, and this is 0, this is going to be -100, and this is going to be 100. It's not even, I apologize. We live at -70 in our neurons, so we're down here. When we say depolarization, it's a decrease in membrane potential. We mean we're going towards 0. We're going this way. If you take this guy and flip it so it looks like this, here's our 0, here's our -70. We are essentially going up. So a depolarization looks like this. The graph goes up. It is becoming more closer to 0, so it's becoming less negative because the negative, let's say we go to here, -50 is less negative than -70. It's very counterintuitive, but it works. So that's a depolarization, less negative, closer to 0. The graph goes up. Then you have hyperpolarization. Hyperpolarization is going away from 0. So here's my 0, here's my -100, here's my -70. We're going this way, further away from 0. It also means that the inside is becoming more negative. The graph looks like this. It is going down. So depolarization is up, more towards 0, less negative. Hyperpolarization is down, more negative, away from 0. So that's what's going on. And it doesn't matter if it's a graded potential or an action potential, those terms work. Okay, so moving on to a graded potential. So remember, these are the short-lived, localized changes that are happening immediately wherever they occur with your membrane potential. So the stronger that stimulus is, the more voltage changes and the farther the current flows. So essentially, the louder, the stronger, the louder. This is triggered by a stimulus that is opening up a gated channel, and that gated channel is going to result in depolarization or hyperpolarization. And a graded potential is named for where it is occurring. So there could be a receptor potential, which is going to be at the receptor of a sensory neuron, so skin, eyes, taking in visual information, in your ears, taking in sound waves, on your skin, taking in tactile touch, on your tongue, your taste buds are taking in taste sensation from ions. All of those are taking in sensory information directly from whatever organ is bringing that information to them. That is going to be a receptor potential. But then you also have a postsynaptic potential, which means the neuron who looks like this, here's my dendrites, here's my axon. We are talking about this guy right here. Your postsynaptic potential is triggering a change in, not in the synapse, but in the neuron that is left. So it's actually, to redraw this guy, happening here at in the dendrites of a neuron. After it picks up communication, it's a postsynaptic because it's after the synapse. This is pre-neuron, this is post-neuron. But that postsynaptic potential is happening in the dendrites of the postsynaptic cell. So that's what's going on with this graded potential. So you can see all of these notes right here. This receptor potential, again, is going to be more in those sensory ions. You can also say that it's the outside of the system, the external environment, bringing information inside of the system to the nervous system. That's where their sensory information comes in. Then you have that postsynaptic potential, which is one neuron connecting to another. We're not going to focus too much on this delay concept, but basically what it means is that if it's not a very strong signal, it doesn't move very far. And it will taper out as it moves down an axon or in a dendrite, wherever it is occurring. So just remember when we're talking about a neuron, this is my general, how it is drawn. These are my dendrites. This is my axon. It's one directional, so communication goes this way. When we're talking about this, think of these like tubes. The cell body in the middle is definitely going to be three-dimensional, absolutely. But think about the axon as a gigantic straw. It's three-dimensional, but it's kind of like a round tubular structure. Think about the dendrites the same way. So that's why this is drawn as a tube. Basically, if you have a tube, it will go either direction from where information occurs. So if information occurs here, it will peter this way. It will also peter this way. However, the farther it gets away, the charge will decay. So that's really what's going on. We're not going to spend a lot of time on that, but it will decay over short distances. So you can see again, this is the active site. This is where we made the signal, and then it decreases as it gets further and further away because it's only for short distances. Okay, so that's a graded potential. That's kind of the focus of that. This section is really focusing on an action potential. And an action potential is again going to be over long distances. And as it's over those long distances, it is also then going to be triggered by signals that are bringing in information. So it is sending out information. Again, an action potential sending out information over long distances. So an action potential will only occur in two types of cells. Muscle cells, we've talked about this with the events at the neuromuscular junction. That was an action potential. And a neuron. That's the only place it happens. These are shorthanded to APs for action potential. And what's cool is that they do not decay. So once it happens and it's good to go. You'll also hear of this as an impulse. That essentially is just meaning that it's an interesting term, but you'll hear it referred to as kind of like an impulse moving down the length of an axon. And it is caused by specific voltage gated channels that are opening. So here's my lovely little neuron, and it is long because these axons can be long. The longest axon is actually going to be from the base of your spinal cord all the way down to the tips of your toes. So an axon can actually be up to like 3 feet long. The longest ones are going to be in your leg. So that communication has to travel a pretty long way. So that is a long distance on an axon. So like we said, 2 key players: sodium channels and potassium channels. Sodium channels are going to have gates, potassium channels are going to have gates, and they're both going to open in response to what is going on in that membrane potential. So when you generate an action potential, multiple things are actually happening. The first thing that is happening with an action potential is going to be the neuron is doing nothing. First step, rest. Nothing is happening. When you are at rest, your neuron is chilling, all gates are closed. Nothing's open, nothing's moving, nothing's happening. Remember, the goal of an action potential is the stimulus is sending a signal down a long distance axon. That signal is because the movement of ions have crossed the plasma membrane and they have changed the membrane potential. And if they change the membrane potential, then it's because a gate has opened or and the ions have moved. So that's kind of like the backup. So now, if nothing is open, everything is closed and hunky-dory, tight as a bug in a rug, nothing's moving, all sodium gate channels, all potassium gate channels are closed. Our neuron is going to be having a resting membrane potential of negative 70 millivolts. We have established that as normal already. So we've got that resting state. We talk about a little bit more. Here is our action potential, and you do need to know the action potential graph looks like this. You need to be able to pick this guy apart and identify every single part of the graph. So this first resting state is actually only going to be, actually let's do this. The first resting state is going to be right here. This is part 1. And with our part 1, we are not really moving anything. Actually, let me get that. Let me rephrase our part 1. Looks like this. It is going to be this part right here. It's a little bit more of that flat. I drew it too curved before. Okay, nothing's moving. Therefore, there is no change. If this guy right here is negative 70, we're not moving up, we're not moving down. Second stage, depolarization. Remember, depolarization means closer to 0, which means things are moving up the graph. So when depolarization happens, it is because the sodium gated channels have opened. Remember, we have a high concentration of sodium out. If we open up our sodium, sodium will move in. Notice we are only talking sodium. Depolarization is because sodium moves. Depolarization is because sodium is moving in. If you have sodium moving into the cell, you are taking a positive ion and moving positive ions into the cell. The inside is going from a negative to a more positive. If you open up a sodium channel and it lets positive ions in and your inside becomes more positive, it creates this cycle where it will then in turn open up another sodium channel and it will move more sodium in and it will become more positive, which will open up a new sodium channel. So you get this cycle. This process will occur until enough sodium has moved into the cell that you hit something called threshold. So threshold is going to be about negative 55 to negative 50 millivolts. Usually negative 55 is like the standard. But when you go from negative 70 and enough sodium enters the cell that you hit negative 55, when you've hit that point, it is considered the process of an all or none. So you are essentially going to open up all sodium channels. And if I am hitting negative 55, I'm going to open everything. And when I open up all of those sodium channels, my inside of the cell is getting so much positive ions coming in that the inside cell is no longer negative 55. That plasma membrane potential is no longer a negative number. It now becomes positive 30. So when we look at that on the graph, here is going to be my action potential graph here. I've had this part. Now we're doing this part. We're going up. We have hit the part that is negative 55, that threshold. Once you hit that threshold, you skyrocket and you are going up the graph all the way to positive 30. That is depolarization. Depolarization is sodium. Now we go to step 3, repolarization. What is happening with repolarization is basically we're going to close all of the gates that were open. So we are going to close sodium. If we close sodium, sodium stops moving. But we're also going to open potassium. So sodium will stop moving, but guess what? Potassium has a high concentration inside of the cell, and he is going to want to move out. So if we open the potassium gates, our sodium doesn't move because it's not related to our potassium. They are separate concentrations. If we open our potassium gate, our potassium moves out of the cell to the extracellular fluid. If it moves out of the cell, we have a lot of positive ions moving out. That means the inside of the cell will become more negative. And as we become more negative, here's our little graph over here. We've done this, we've done this. Now we're on this downward slope here. We are becoming more negative. Remember? Yes, we're doing more negative. And eventually it will go all the way down until you actually hit that baseline, that resting membrane potential of negative 70. So basically in the repolarization stage, you go from a positive 30 millivolts to a negative 70 millivolts. Cool. Repolarization is because of potassium. Potassium is moving, sodium channels are closed. And then you have step 4, hyperpolarization. So remember, hyperpolarization is going away from that resting membrane potential. It's going away from 0. So what's happening in hyperpolarization is some potassium channels are closing. But these are going to be like those lovely little things you can put on your kitchen cabinets that slowly close a door rather than having it slam shut. So hyperpolarization, potassium channels are going to close, but they are slow. So there's still some leak of potassium happening. So there is some potassium still kind of leaving the cell. But remember, all sodium channels are still closed. No change. So if we have some potassium leaving the cell, basically that means that our membrane potential will go below resting membrane potential at some point. So if this is our resting membrane potential, draw that a little higher, right there, it will actually dip below because more positives are moving out. It goes below negative 70. This is your action potential. So your biggest takeaway from this section is going to be this figure 11.2. Be able to draw this guy. Know the action potential. Know the whole process. Be able to draw it. Be able to pick it apart. This guy right here is going to be your friend. So real quick, negative 70 is our resting millivolts, is our resting membrane potential. All channels are closed. When we start opening up our sodium channels, we will have sodium move into the cell, which means positives are moving into the negative. So we are going closer towards 0. This is going to occur once we get to negative 55. It is going to open up all of the sodium channels. and it's going to rapidly depolarize to positive 30. Sodium and depolarization is happening here. Once we get to positive 30, sodium channels close, potassium channels open. If potassium channels open, they are going to move out of the cell, taking all that positive ion with them. You're going to get a repolarization, or a more negative, and it'll go from positive 30 down to negative 70. But this is because potassium channels are open. Then there's going to be a little sweet spot where potassium channels start to close once you hit negative 70. However, they're slow. So for a period of time, we have hyperpolarization because our potassium channel is still letting some ions out. So we're going to go below our negative 70. And eventually, when they all close, we're just going to go regular back to baseline. So this is our action potential. This is what we need to know. This is a big takeaway. So repolarization is going to reset electrical condition. It goes back to negative 70. But our ions are still imbalanced. So that's why our sodium-potassium pump will actually put them back in play. So it's a lovely little cycle of how it all works. So again, with our resting membrane potential, the concentrations of potassium and sodium on either side are different, and they're controlling this whole thing. Okay, another premise of an action potential is going to be something called all or none phenomenon. And an all or none phenomenon is essentially kind of what's driving an action potential behind it. So not every time we have depolarization. So not every time we do this will we get this. Not every time. So it is not going to be that every time you get depolarization, you get all the way to an action potential. So what happens if we just go this little section right here? That is called this all or none phenomenon. So not all depolarizations will cause an action potential. So it may be a little bump, but if it doesn't hit negative 55, it doesn't trigger the all or none phenomenon. When you'll hear about an axon firing, which basically means an action potential has occurred, communication has occurred. When that happens, you've hit that negative 55, the magic threshold. It is going to bump up to positive 30 because sodium is rapidly moving into the cell, and you're going to get this all or none phenomenon. Basically, it doesn't happen if you don't hit negative 55, but once it does hit negative 55, it will always hit positive 30. There really is no in between. So it's called threshold and then all or none phenomenon. Okay, another term you're going to hear is called propagation. We talked about this with the muscles when we talked about propagation of an action potential down the sarcolemma. So propagation is basically you're going to move this action potential down the entire length of an axon. So remember, I said that the longest one in the body is almost 3 feet long, goes from your base of your spinal cord all the way to the tip of your toes. And there's one that goes back from the tips of your toes all the way to the base of your spinal cord. Propagation allows for this action potential to essentially go all the way down the length of the neuron. So the way it does that is it will actually, an action potential occurs right here. It's called the axon hillock. And this is where it will start. And then it will cause a rapid change in the membrane potential here. And then that will essentially cause all of the sodium ions here to change. And then this will cause all of the sodium ions here to change. And then this will cause all the sodium ions here to change. And essentially you move and update and fix and cause an action potential to occur all the way down the length of a neuron. And you're going to have this propagation phenomenon. So basically that is what is going on. Once you trigger that action potential at the axon hillock, it will self-propagate and keep going. One thing to note, this process will only occur in a non-myelinated axon. So just keep that in mind. We're going to talk about that in a little bit with that non-myelinated axon. And also remember that an action potential only occurs down the axon. It will never go backwards up to the length, up to the cell body. It's one directional and one directional only. So these graphs are showing the propagation. They're showing how it's changing from here to here. I don't It's hard for me to read these graphs and understand that, so we're just going to skip those for right now. You don't need to draw or understand that. You do need to draw an action potential. Okay, there's another term that we're going to talk about real quick, and that's going to be called conduction velocity. And basically, conduction velocity is referring to how fast the communication flows. Conduction, how fast the speed of transmission is going to be. And when we have this conduction velocity, it's going to be based on the stimulus of the action potential. So whenever we have a super strong stimulus strength, so this guy right here is going to show that the stimulus is right here. If the stimulus is right here, you're going to have this much action potential. But you could also have this much stimulus strength and you're still going to have that much action potential. So it's going to be the relationship between that stimulus strength and the action potential frequency. You're still getting the action potential, but the difference between the two is this, I drew over it, so let me erase it, only has 4 action potentials. This was higher, so it has more. So it's not that the signal strength went greater here, it's that it went greater volume-wise, frequency-wise, it went greater there. We're not going to spend time on refractory periods, so you don't need to really focus on these. Basically, it's after an action potential occurs, you need a little bit of time before you can trigger another one. You have to reset to -70 and then pause. That's basically what that is. Okay, so back to that conduction velocity. I got a little ahead of myself there. How fast that the transmission is going to occur down the length of the neuron. 2 things are controlling speed. One is the axon diameter. Remember I said think of these as a tube, so it's whether or not it's going to be one of those cute little straws that we're all used to, or one of those like smoothie type straws, or a garden hose. Axon diameter, the larger the diameter, the faster it moves. Physics is going to be saying there's less resistance, there's less plasma membrane to actually deal with. The other thing that's causing the transmission to go fast is the degree of myelination. So way back when, at the beginning of the chapter, we talked about myelination being the fatty sheath that is wrapped around the axons. That fatty sheath, if it exists or it doesn't exist, will determine how fast this guy will move. And the presence of that myelin will either give us a fast or a slow, and it will give us something called continuous conduction or saltatory conduction. So first one, continuous conduction is going to be what is called a non-myelinated axon. There is no myelin. This is also going to be slow. This does not happen fast. And when this is happening, your voltage-gated channels are right next to each other. They are back to back. They are adjacent. So when you have continuous conduction, basically, you're going to have, let me find him. Okay, here's your, let me go back to this one. If this is going to be an action potential and it just happens right here, like we said, we're going to have that decay. It's not going to continue for very long. But if we have an action potential, and like we said, if we open up, here's sodium, 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 sodium. If we open up these sodium channels, we're going to get ongoing action potentials down the length. But the reason this is slow is because you are having to do that entire action potential process every step of the way. That's non-myelinated. It's continuous conduction. The one we like is saltatory conduction. And saltatory conduction will happen in myelinated axons, and it is fast. But there's also going to be myelin that is occurring and causing this. So myelin essentially will insulate the electrical signal. So basically what will happen is rather than having a sodium channel here, here, and here, 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 and here, what it does is it's got that myelin wrapped around this whole section, so your sodium channel can only be here. And then we've got this whole thing wrapped. So your sodium channel is going to be here, and then this whole thing is wrapped, and you only have a sodium channel here. So basically what it's doing is it's causing your stimulus to occur here. Rather than having that sodium channel all the way down, it is essentially protecting the signal, and you only need sodium here, and it jumps. It's 30 times faster to have saltatory conduction than it is continuous conduction. So it's very, very cool. How this actually rings true is in the diagnosis of multiple sclerosis, MS. Multiple sclerosis is an actual definition where it's autoimmune, and what's happening is that the body is attacking the myelin itself. So if the body is attacking the myelin, you do not have myelin around your axons. Therefore, you get slow nerve conduction. You get slow action potentials. If you don't have any myelin, then you will get that decay of signal. And basically, what will happen ultimately with multiple sclerosis is the impulse conduction, that action potential will slow, and eventually it will cease completely. If you do not have an action potential, you do not have movement of your muscles. If you do not have an action potential, you do not have chewing food. You do not have the ability to process nutrients, to drink, to breathe, to eat, to talk, to move. At the end of the day, if you do not have control of a muscle, you do not have control of your diaphragm. You don't have control of your esophagus. Multiple sclerosis is a debilitating disease because it will essentially slow you down so you stop all movement. If your muscles stop, if your diaphragm stops, multiple sclerosis does eventually end in death. So that is the clinical ramification of this concept that we are talking about right now. One thing with this conduction velocity, to wrap up this section in this chapter, is going to be the nerve fiber itself, or the axon, is going to be classified based on whether or not it has that myelin, whether or not it's going to be skinny or big, the diameter, and it's going to be that will give you how fast the thing goes. So when we say nerve fiber, we mean nerve axon. So there's 3 different types. You're going to have a group A axon or group A fiber. These are going to be normally your muscle fibers, your somatic nervous system. They are large, very, very big, and they have a lot of myelin. Therefore, they are fast, 150 milliseconds. You want fast when you're moving your muscles. Makes sense. Group B is going to be mainly your autonomic nervous system, so your glands and your muscles. They are lightly myelinated. It's not none, but it's not thick. So they're like middle of the road speed, 15 meters per second. So if we've got our race car in group A, this is going to be your moped. 15, this is not even just this is not a car. This is like a legit moped, the difference between the two. 15 meters per second. And then you've got group C. And group C is going to be also for your ANS and for your glands and muscles. These are going to be considered non-myelinated, and they have the smallest diameter. These are skinny, like a string. Because of that, they are the slowest ones out there at 1 meters per second. So a group C is going to be you walking from point A to point B. Group B will be you taking a moped from point A to point B. And group A is going to be the most efficient of them all, where you're riding the sports car from point A to point B. So that's kind of how it works, but it's based off of diameter and myelination. The conduction velocity will be determined based on that. So that is it for part B.